and waves are not going to be asked on the exam. So when we get to question 24, you guys don't necessarily have to continue with the review unless you want to. But he said specifically that he's not going to ask things like this. I included them, though, in case people are not from Dr. Velasaris's section. So just as a review. So that being said, let's go ahead and get started here. So the first 6 questions are all in reference to this RLC circuit described here in this nice, beautifully stated statement. Says the inductor has a reactance of 75 ohms and an inductance of 225 millihertz, a 45 ohm resistor, and a capacitor C, whose reactance is 85 ohms, are also in the circuit. And the RMS current in the circuit is 1.75 amps. So for questions like this, I always like to just write out everything on the side just to get an idea of what numbers I'm working with. So I have an inductor with reactance of 75. Inductance of 225. Resistor of 45. And capacitor is unknown. Reactance of the capacitor is 85. And then we have a current, RMS current, of 1.75 amps. So the first question is asking what the impedance of the circuit is. And the formula for impedance is Z equals the square root R squared plus XL minus X sub root C squared. And then from here, we just simply plug in our numbers. Which will give us 46.097, and we'll round up to 46.1 ohms. Next question is asking what the RMS voltage of the source is. So to do that, we use a variation of Ohm's law, which is V equals IZ. And then again, we just plug in our numbers. Our current is 1.75 amps. And then our impedance is 46.1 ohms to give us an RMS voltage of 80.7 volts. You guys good so far? You guys have any questions about anything that I write, or if I leave anything out, don't hesitate to ask. Next question asks, what is the capacitance C? So we know that the reactance of the inductor is equal that, which is equal to 75 ohms. So we're going to rearrange this equation. Don't forget, our inductance was given to us in millihertz, so we're going to have to convert that back to hertz. And then likewise, plugging that value into the formula for inductance of the capacitor. $28,330.5 equal to 1 over C. And just take the inverse of that value, and you get 3.53 times 10 to the negative fifth, which is also equal to 35.3 microfarads. You guys go with that? Next, we're going to solve for the voltage amplitude across the resistor. And this is also this Ohm's law. V equals IR, plug in the current, 1.75, and the resistance of the resistor, which is 45. We get 78.75 volts. Yes. Voltage amplitude across the inductor. Same thing, except we're going to use the reactance of the inductor. Guys good? Next question asks what the voltage amplitude across the capacitor is. And if you guys could have guessed, same thing we've done the previous two. Fine. Moving along, series AC circuit has a resonance frequency of 8.2 kilohertz. If the inductor in the circuit has a value of 4 hertz and a resistance of 60 ohms, what is the capacitance of the circuit? So the formula for resonance frequency looks like this. And we know that that is equal to 8.2 times 10 to the third. And so I'm just going to rewrite it. Know that our inductor has a value of 4. Put that in, and then C. So solving 2 pi times 8.2 times 10 to the third equals 51, 5, 2, 2.1195. Taking the inverse of 51,000, we get 1.94, 1 times 10 to the negative fifth, equal to the square root 4c. And then we square that value. To get 3.767 times 10 to the negative 10th equals 4c, and then divide that by 4. That should give you a value of 9.42 times 10 to the negative 11th farads. You guys good? All right. That's about it for RLC circuits. Now we're going to start going into review. A charge Q is placed at the origin. Point A is 1 micrometer from the origin, and B is 3 nanometers from the origin. What is the ratio VB over VA of the electric potentials at the 2 points? So it's pretty much telling you how to solve this by giving you this ratio here. And remember that potential equals K times Q divided by R. So we don't have Q, and K is a constant. So we'll do K Q over RB divided by K Q divided by R. Okay. The terms will cancel. And 3 times 10 to the negative 9th divided by 1 times 10 to the negative 6th. So we got 1. Plugging that in gives you a value of 1,000 divided by 3, making the answer D. Everyone okay? Number 9. A horizontal coil having 156 turns and a radius of 1.2 centimeters carries a current of 1.20 amps. If it is placed in a uniform 2.5 Tesla magnetic field, what makes a 25 degree that makes a 25 degree angle with the plane of the loop? The torque on the coil is what? So one thing to highlight here is angle with the plane of the loop. Because that makes a difference. And in order to correct it, because right now it's giving you an angle with regards to the plane of the loop, but we want the normal. We want the normal angle to the magnetic field. So what we do is add 90 degrees to 25. And then likewise, we just refer to the equation, and A B sine theta equals torque, and then plug in. Times area sine 115 equals 0.19 joules times meters. So let me just double check the math, make sure everything's right, so you guys can too. And for this equation specifically, sorry, I should have changed the units here to meters, but if you calculate it either way, you'll still get the same answer. But just for sake of safety, always convert your units. Bless you. Any questions on that one? So a battery, a loop of wire, and a switch make a circuit that produces a counterclockwise current. A second loop of wire sits directly below. What can we say about the current in the lower loop immediately after the switch is closed? So one way to kind of help visualize this is to draw the circuit. So that's going to produce a counterclockwise current. And then you have a second loop sitting right below it. And that is going to produce a clockwise current. If the current in a wire is quadrupled, by what factor will the magnetic field distance R away change? So let me use equals not I, we're doing quadrupled, so I'm multiplying I by 4, and then divided by 2 pi r. So based on this, you can see that it's going to increase by a factor of 4, but if you want to pull it out just to double check, you could also look at it like this. Number 12, a proton is projected with a velocity of 3.5 kilometers a second into a magnetic field of 1.2 Teslas perpendicular to the motion of the proton. What is the force that acts on the proton? So, we are going to use the equation F equals Q V E. Give you guys a little visual. You have a proton, perpendicular. These up arrows are indicative of the magnetic field, and then this horizontal arrow is indicative of the velocity of the proton. And one thing that I know Dr. Villasaris will most likely do is if he gives you guys like a proton or electron, he'll give you the charge, because I know that that's not included on your formula sheets. And I know in the past he's done that on one of the exams. But if you're in a different class section, I would check with your professor. When I took Dr. Kara, I know he did note cards, so I would include those values on the note cards just in case. Really just depends on who you're taking the exam with. But that being said, the charge of a proton is equal to 1.6 times 10 to the negative 19th. Plug that in. There's velocity. Times the 1.2. Which will give a value of 6.7 times 10 to the negative 16th newtons, and that would be option B. The next question says a proton. I'm sorry? It's still the same charge. Mass would differ. Yeah. Yeah. A proton is projected with a velocity of 3.5 kilometers a second into a magnetic field of 1.2 Teslas parallel to the motion of the proton. What is the force that acts on the proton? Keyword in this question is parallel. And when it's parallel, there is no force that will act on the proton. Example of how to think about that is if you were to take a piece of paper and if you were to hold it in a field while the arrows are going parallel to it, they're going to go around the piece of paper. There's no force acting on it. You guys good? An electron moving perpendicular to a magnetic field of 3.7 times 10 to the negative 2 Teslas moves in a circle of radius 0.5 centimeters. How fast is this electron moving? So just give you guys a little diagram. Then we are going to use R equals mass times velocity divided by charge times magnetic field. So, mass of an electron is 9. I'll put that over here. 9.11 times 10 to the negative 31st kilograms. And then charge, same as proton, 1.6 times 10 to the negative 19th coulombs. Magnetic field, B equals 3.7 times 10 to the negative 2 Teslas, and radius equals 0.005 meters. Then, once we have all that written out, it's just plug and chug. Sorry. After we rearrange the equation, we will plug and chug. So we're solving for velocity, so we're going to rearrange this. R times Q over V is going to equal R times Q times B over M. Now we can plug and chug. And that will give you an answer of 32.5 megamilliseconds. Mega being times 10 to the 6th. So just do the space. Number 15. Charges are placed at the four corners of a square. Side equals 1 millimeter. Excuse me. One electron is placed in the right lower corner. One proton is placed in the left lower corner. Excuse me. Two electrons are placed at the left lower corner, and two protons are placed at the right high corner. A proton is then placed at the center of the square. What is the direction of the force on the proton at the center? So, let's do this one. It's easier to draw it out. It's a square, so just make sure all the sides are equal. It says we have one electron is placed in the right low corner. Just a negative sign. One proton is placed in the left high corner. One positive sign. I'm sorry, put that in wrong. one electron is supposed to be on the right. 2 protons are placed at the right high corner. And then 2 electrons at the left low corner. So just add another minus there. So that's what it's asking about, and you're placing a proton in the center. What is the direction of the force on the proton? Simple way that I like to do this is to just kind of give your own increments. So 1 proton, let's say, will go half the distance. And then this electron down here is going to pull it half the distance as well. And then, because you got 2 protons, you're going to have an arrow that's twice as long. And then, because you have 2 electrons, you have an arrow that's going to go twice as long again. So, based on this diagram, which way do you guys think it's going to go? Very good. So that's going to come down that way. Next question has to do with polarization. Sorry, not this question. But it does have to do with light. How many wavelengths of violet laser, lambda 400 nanometers, fit inside of a tank? The laser is fired directly into the tank. Assume the laser travels 30 centimeters inside the tank and is filled with an oil that has a refractive index of n equaling 2.5. So, come back to this. Lambda naught over n equals 400 nanometers over 2.5. We get a wavelength of 160 nanometers. And then number of waves is equal to distance 30 centimeters divided by the wavelength 160 nanometers, and converting to proper units. We get 1.87 times 10 to the 6th, and then rounding up, you can find 2 times 10 to the 6th. So the answer to that one is D. Guys good so far? Number 17. A constant magnetic field of 1 Tesla is applied to a rectangular loop of area 4.5 times 10 to the negative third meters squared. The area of this loop changes from its original value to a new value of 1.5 times 10 to the negative third meters squared in 6 seconds. What is the EMF induced in the loop? So we are looking for EMF. We're given a magnetic field area. Over delta T, which is equal to B times A divided by delta T. And then once we get that, it's just plugging it in. Reduce to 1/2 times 10 to the -3rd. I'm sorry. I have it right. Answer is B. So yeah, it would be 0.5 times 10 to the 3rd, because the units are millivolts. You guys good? A rectangular loop of wire carrying a 4 amp current and with certain dimensions is placed in a magnetic field of 0.6 Teslas. The magnitude of the torque acting on this wire when it makes a 60-degree angle with the field is 1.1 newtons times meters. What is the area of the loop? So we're going to go back to our torque equation. Theta, and we're looking for the area, so we're going to rearrange this to A equals torque divided by current B sine theta. Then our current is 4 amps. B equals 0.60. And theta will be 60 degrees. And the torque, 1.1. Plugging that in. meters squared. Rounding up, you can get answer B, 0.53 meters squared. Number 19, a conducting loop of wire has an area of 150 centimeters squared and a resistance of 12.5 ohms. There is a magnetic field of 100 teslas perpendicular to the loop. At what rate must this field be reduced to induce a current of 0.1 amps in the loop? So, I'm going to begin by writing out our givens. Then we're going to use V equals R. Rearrange this one more time. As you can see, our answer options are in Teslas per second, Teslas per second. So now we just have to plug it in and calculate. And you'll find that after doing that, you get 83.3. Number 20. A rectangular coil lies flat on a horizontal surface. bar magnet is pulled away from the center of the coil with its north pole pointing down. What is the direction of the induced current in the coil from an overhead perspective? So let me just move this down. Rectangular coil, bar magnet, north, south end, and it is going this way. So what is direction of the induced current in the coil from an overhead perspective? What do you guys think? It is going to induce a clockwise current. Number 21, a vertically polarized light wave of intensity 1,000 milliwatts per meter squared is coming toward you out of the screen. After passing through a polarizing filter with a polarizing axis of 25 degrees from the horizontal, the wave's intensity is. So, important to highlight in this question. Say that this is your polarizer. Sorry. This is your polarizer screen. And Y is the polarizing axis. It's a little crooked. This is the angle we're looking for. But as you see from the question, it's giving us 25 degrees from the horizontal. So how can we fix that? Just take the angle that we're given and subtract it from 90, which would give us a 65-degree angle. So theta equals 65 degrees. And then we're going to use the equation for transmission, which is I Then after that, it's just plugging it in. I'll give you a value of 178.6. Equals 179 milliwatts per meter squared. E. So one thing that you guys should look out for is on equations or questions that are asking for torque and polarization is what angles you're given, because we're only using specific angles, and especially during exams they like to try and trick you and see if you can figure it out and determine whether or not you're given the appropriate angle to be plugged in. So just be cognizant of what angles you're given and the wording of the question. Right. So number 22. A solenoid of 150 turns carrying a current of 1.5 amps has a length of 50 centimeters. What is the magnitude of the magnetic field at the center of the solenoid? So we're going to use the equation for the magnetic field of a solenoid, which is the solenoid is equal to mu naught times current divided by length. We see that N equals 150. Current is 1.5 amps. L is 0.5 meters. And mu naught is a constant. Which would be a wire carrying a 4 amp current is placed at an angle of 60 degrees with respect to a magnetic field of strength 0.2 teslas. If the length of the wire is 6.6 meters, what is the magnitude of the magnetic force acting on the wire? So, let me start off by pulling out what we're given. force we're going to want that will equal 0.4156 newtons, and B will be our answer. Number 24 says Coulomb's law describes what? Say D. Force between 2 point charges. What do you guys think? Yeah, that's correct. So from here, if you're in Dr. Velasar's class, you don't need to worry over these next three questions just because he said specifically that he wanted me to take them out, but because I am doing this for all sections, I have to include coverage of that material as well. So this is what he told me. He told me to take these out, assume that you guys don't have to know it. The last three, yes. You'll still need to know polarizers and what he covered as far as you guys went with the lights, but this is not something that he covered in class for you guys. He didn't have time to make it this far. My pleasure. Good luck, guys. So 25 says light rays from an object travel through a pinhole. The rays reach the other side and form what type of image? Best way to go about this. So, based on the image, it's going to be inverted and real. Number 26, a double slit experiment uses coherent light of wavelength 633 nanometers with a slit separation of 0.1 millimeters and a screen placed 2 meters away. What is the distance on the screen between the first order and second order bright fringes? So for this equation, we use y equals lambda divided by d lambda L. And that's going to be equal to 633 times 10 to the negative 9th times 2 divided times 10 to the negative third. And that gives value of 0.01266 meters, which is equivalent to 27 millimeters deep. How much time do we have left? So I got a good amount of time. After this, I'm going to be going over, I can go over more stuff. I was going to do capacitors and resistors in series, just to give you guys a refresh on that in case you want it. But if not, you're welcome to leave. 27, a diffraction grading is to be used to find the wavelength of the emission spectrum of a gas. The grading spacing is not known. The light of a known wavelength of 615.3 nanometers is deflected by 42.1 degrees. In the second order, by this grading, light of the wavelength to be measured is deflected by 35.3 degrees. In the second order, what is the wavelength of the light that is to be measured? So, use d sine theta equal to m times lambda, where theta 1 equals 615.3 times 10 to the negative 9. Theta 1 equals 42.1 degrees. M equals 2, second order. So, using d sine theta, we're going to solve for d. That's 2 times the wavelength, theta, or lambda 1. And solving for d, we get 1.8355 times 10 to the negative 6th. Now we're going to turn around and plug that into the same equation, but using the numbers for the second light. So that gives a value of 1.06, 07, times 10 to the negative 6. Divide that by 2. And 5.303. Which is equivalent to 530.3 or 530, which is B. So that concludes the review portion, or the review guide portion at least. Since we have extra time. There we go. All right. All right. So would you guys say that these are in series or in parallel? These two right here, 90 and 45. Parallel? Very good. So, I'm going to take these two and move it over like this. We're going to combine them into one. We've got our 10, 60, and then how do we add resistors in parallel? Very good. So it's going to look like 1 over CEQ equals 1 over C1 plus 1 over C2, 1 over 90 plus 1 over 45. Gives you 1 over 30. So we know that this is going to be 30 ohms once we take the inverse. Then next we have 2 resistors in series or parallel. Very good. So we're going to take these 2. Combine them again. And how do we add resistors in series? Very good. They just add together. So that'll turn into 40 ohms and 60 ohms. And then these last 2, series or parallel? Oh. They are in parallel. So to add these 2 together, add 1 over 40 plus 1 over 60, and that will give us 24 ohms. You guys okay with that? Yeah. So these are in parallel. These were in series. And then these 2 were in parallel. Physics 2. So, how would it change if we replace the resistors with capacitors? It's still going to be solved the same way. So we know that these 2 are in series or parallel, sorry. But unlike resistors, we add them the opposite way. So when they're in parallel, they're not going to be added one over each other. They're added like they would be, like resistors would be in series. So this is going to give us a new capacitance of 135 with 10 and 60. We got 1 over 10 plus 1 over 135. That gives us a fancy number of 9.31. And 60. So, adding these last two together would give us 69.31 farads as the total capacitance for that circuit, if we were to use the same values as the previous one, just to show you a comparison of the two. Just to do a refresh on magnetism, this is from this textbook here, College Physics by Knight, Jones, and Field. And the question asks, does the compass needle rotate? What do you guys think? What do you guys think? I hear no. Clockwise? Counterclockwise? So the answer is C, not at all. I'm sorry? No, it's because the positively charged rod is not going to induce a magnetic field. If it were a magnet, though, the story would be different. But because it's a charged rod, it just has charges allocated at one end, and the charges aren't leaving the rod unless they make connection with an object. So it's a stationary charge. No, if it were a stationary magnet, it would rotate. I'm not familiar with the labs, so I can't say. Do a question here to brush up on right-hand rule. Where is it? Here we are. So the figure shows an edge view of a current loop using what you've learned in figure 24.15, the figure right above. Which arrow gives the direction of the field in the center of the loop? So it's kind of hard to see, but this is a dot, and that is an X, and those circles right above. So using the right-hand rule, well, first let me ask you guys, what is the difference between a dot and an X? Which one signifies what? Which is it? Very good. So X is going into the page, and the dot is coming out of the page. A fun way to think about it is if you were to look down at a piece of paper and try pushing your pencil through it, it'll kind of form like an X where the pencil tip is. And then if you were to do the same, you're just going to get a dot of the pencil tip coming through the paper. And that would be coming out at you. So, using the right-hand rule, fingers are current or velocity or magnetic field. So just to right-hand rule for fields. So your fingers are going to curl in the direction of the magnetic field lines, and the thumb is going to be current or velocity. Back to the equation. So into the page would be the direction of our current. So if you were to take your thumb, point it down, and kind of come around, the magnetic field is going to be wrapping around in which direction? Another way you could do it is if you were to, because you know that this is coming out of the page and back into the page, you know that it's a loop, you know that it's going to do like a little curve. So you could also do the right-hand rule in that way, which would be, it's very close up with my hand, but looking at it like this, I'll come stand in front of it. would be like this. Because it's coming out of the page and back into the page. So your thumb's running along the direction of the current, like it is in the photo, and your fingers are going to point in the direction of the magnetic field. So based on that, which arrow do you think is indicating the correct direction of the magnetic field? C? A? What do you think? So your fingers are going to be pointing up. In theory, they would, because it's going to be forming a circle, but the direction in the center of the loop. So around the whole loop, it's doing that clockwise, this clockwise motion around the ring. And in the center, it's going to have a straight direction, as shown by this figure right here. Does that make sense? You guys good in the back? Yeah? It's going to be A. Yes, I think mine was different than the question in the book, but it was a similar, I guess, form of asking the question. Yeah. So to go back to compass, compass is placed above a long wire when a large current is turned on in the direction shown. In which direction will the compass point? What do you guys think? Use the right hand rule for this one. So point your thumb in the direction of the current. And which way are your fingers initially pointing? This is going to form a circle around the loop, or around the wire rather. See? The compass is placed above the wire. Let me think of how. So imagine as if you're looking down on the wire. It's going to be forming a circle. So right here, the magnetic field is coming out of the page, and right here, the magnetic field is going into the page. So following the lines of the magnetic field, which direction do you think the compass is going to point? A, B, C, or D? What do you guys think? D? Is it not D? What do you guys think? Over here. Up front? Anybody else? No? Yes, it is D. So, don't doubt yourself. Because with physics questions, you have to be very careful with the wordings of the questions. A compass is placed above a long wire, and when it says above the long wire, you have to just kind of assume that you're looking down on it. And once you assert a position in space that you're going to be approaching this problem, you have to then define the parameters of the magnetic field. And doing that, you know that, because the magnetic field's a circle, it's not a straight line in any which direction when you're using the right-hand rule. So it's going to be wrapped around the wire, and because it's going like this, it's going to point it up. How do you guys feel about that? Good? Cool. So, induced currents? Sure. Okay. So this is kind of a standard, just general question regarding it. A square conductor moves through a uniform magnetic field directed out of the page. Which of the figures shows the correct charge distribution on the conductor? So for this one, you're going to want to use the right-hand rule, but not the conventional one that is your fingers curled. This one's going to be how I was taught, was the 3-finger rule. I know that there's some slight variations that were taught in lab, which we kind of addressed in SI, just to show you the right-hand rule that I am utilizing for this. Comes from this book. Is this one. This is not your textbook. This is the college physics by Knight, Jones, and Field. It's just another variation of the same textbook. This one is not provided in the one that you guys were given, which is why there's some slight variations, but it's all generally the same thing. I personally like this method just because it's the first method that I was taught, so to me, I understand it better than other methods. But as you can see, your middle finger is the force, your thumb's the velocity, and your index finger is going to be the direction of the magnetic field. So using that and applying it to this question, thumb's the velocity, fingers the magnetic field, and then your middle finger is the force, and it's going to be like on a right angle perpendicular to the field, magnetic field. So it's a circle, so we know that it's going to be pointing out at us, and it's going to be up. So if you're going to have to kind of turn your finger, or your hand rather, and point it at yourself. And the middle finger is going to be the direction of the force. So based on that, where would you guys say the charges are going to accumulate? At the top, the bottom, nowhere, the left, or on the right? So you're saying E? Either D or E. The green arrow is velocity. So the box is moving through the magnetic field, and as it moves through, it's inducing a, I guess you could say current, but not, yeah, force. Very good. So yeah, you're kind of, the force is going to point in the direction, so it's going to point towards the positive charges. Very good. I'm sorry. So the magnetic field is what you're going to want to pay attention to, because your finger is going to point in the direction of the magnetic field. So those magnetic field lines are, in theory, coming out towards us, and so that you would just point your finger in the direction that the magnetic field lines are going. Right, so the answer is E. You guys want to do some more right-hand rule with, or magnetic flux? Like this? All right. So for these, just a little flashback from when I took physics, I had to draw these out over and over again in order for me to understand which directions they were going to go. That's just how I learned it. It was kind of like forcing it into my memory, which directions it's going to go based on the movement of the magnet. But yeah, so there was, I thought there was more on that. Okay. So the question asks, a magnet is below a coil as shown at right, referring to figure 25.13, the one right above it. For guidance, what is the direction of the induced current in the coil? If the magnet is moving toward the coil, the magnet is held stationary near the coil, the magnet is moving away from the coil. So, where do you think it's going to go if the magnet moves towards the coil? So it's going to be going up. Think of the right-hand rule that we just did with the ring, where it's coming in and out of the page, and at the center of the loop, it's a straight line. So think of it, this is coming down, the magnet's moving down, so in the center, it's going down, but we know that in theory, it's wrapping around the ring. So if it's going up, it's wrapping around the ring. It's hard to draw 3D. So what do you guys think? So it, okay, I see what you're getting at. Yeah. It all has to do with flux, which is that just due to sake of time, there's only, what, 10 minutes left. I don't have, like, the time to go into depth on flux, but yeah. I mean, the best thing I can say is to just study this, because that's how I did it, was just pretty much memorizing this portion. So, if the magnet is moving towards the coil, where would you think that it's going to go? Clockwise, counterclockwise? Yes. Clockwise? Very good.
Isn't it depending also what, like, portion of that you can run the jaws for?
It does, yes.
That has to do with, like, the lines that you draw those.
Yeah, so these are in reference to the direction. So, like we were just saying with magnetic field lines, you're going in the direction of the magnetic field. It's the same with magnets. So if the magnet's north, or if it's south, you'd want to do the opposite of what it would be doing if it was north. If that makes sense.
Like, if we flip them that around, like where south is going in, it would be going counterclockwise. With the same thing going in towards the south, was facing the coil, it would be going counterclockwise.
If it's going in the same direction and you flip the magnet around, you flip, yes.
Clockwise, but flipping counterclockwise.
Yeah. So, do you guys have any other questions? Preferably. Belisarius tips. He says to study the questions in the back, the multiple choice. I'd go for the more challenging problems. Don't practice the easy ones, because after looking at his exams, you just want to be prepared for whatever he's going to ask. I know that he gives, he doesn't go into too much detail within the chapters that he gives you guys, so I would just say know as much as you can about each chapter. He did say, he did mention Lenz's law, and I know he intended to put questions about Lenz's law in the last exam, but I don't remember the last exam if he did Lenz's law on that or not. So I know that that's something that I would pay attention to this time and definitely make sure you know going in. And other than that, for certain things, certain concepts by this point, if you aren't familiar with them, your best bet is to try and memorize them, because just with 2 days' time to try and teach yourself a concept and then practice everything else is, I think, a little challenging. At least for me, that would be. So at this point, what I would do is just kind of try and memorize certain things that try and fill in the gaps. He said that he was going to try and make this one more math-based. He wanted to step away from the concept questions. But that being said, I don't know what's on the exam. I can't tell you anything because I know as much as you guys do. I'm just taking the information and trying to give you my interpretation of it. So he could ask concept questions. I wouldn't expect a lot of them because he wanted to do more math. But with 45 questions, I mean, you do have 3 hours, but 45 questions, I think, is sufficient for 3 hours. So, I mean, it could be anything, really. You guys have any other questions? No? All right. Good luck, guys. I wish you the best of luck. My pleasure. Good luck.